In this section, we're going to talk about an important theorem. It's the monotone convergence theorem. And we'll use this theorem to prove a couple of different results in this course. And you should have actually seen it before in your calculus class. Before I introduce the theorem, I just want to point out some motivation. So recall that a bounded sequence need not converge. It could still diverge due to oscillation. Keep in mind there are two ways for a sequence to diverge. It could either diverge to infinity or it could diverge due to oscillation. And if your sequence is bounded, it's impossible for the sequence to diverge to infinity because we know that there needs to be some set window, negative m to m, that our sequence appears in. All terms have y values that are in the range between negative m and m. Now this is different from convergence because convergence says you should be able to sort of squeeze the window in which you're looking, the epsilon band. You should allow epsilon to shrink to 0 and then always be able to find a way to trap the tail in that location. Here, m is fixed. Nothing is getting squeezed. And so there's all this wiggle room. So you can, bounded sequences can still diverge due to oscillation. So then the motivating question for this section is, what additional condition could we require for a bounded sequence to converge or impose? So what additional condition could we require to guarantee that a bounded sequence converges? Well, if we don't want to oscillate, that means we should eliminate the ability for your sequence terms to sort of go up and then go down and go up and then go down. And as you may have guessed, based on the name of this section, if we impose monotonicity, so that means we require that our sequence terms always be increasing or always be decreasing, then being bounded will require the sequence to necessarily converge. So here our answer is monotonicity. So we want to be increasing or decreasing, but not both. And so if we're going to introduce these words increasing and decreasing, we should give a precise definition of what we mean. So definition, a sequence A sub n is increasing provided that an is less than or equal to an plus 1. So every time you move down your list, and this has to be true for all n in the sequence, every time you move further down your list, you either stay the same in size or you get larger. And so here increasing does include the case where it does allow for your values to stay constant. That is just a definition choice. You might say strictly increasing if you wanted to communicate that the terms are not remaining constant, that they're only getting bigger at each stage. And we would say it's decreasing provided that an plus 1 is less than or equal to an for all n. And then we say an is monotone, provided it is either increasing or decreasing. And a fun fact, technically constant sequences can be classified as monotone because they satisfy these inequalities, because the inequalities are inclusive. So, fun fact. Constant sequences are both increasing and decreasing. So the monotone convergence theorem, which we abbreviate MCT, assumes that you're working with a monotone sequence, and it says if that sequence is bounded, then AN converges. So being monotone together with being bounded guarantees convergence. Without monotonicity, bounded sequences need not converge necessarily. So then the question is, what does the sequence converge to? So what does AN converge to? Well, let's look at a picture. If I have a sequence that is bounded, I know that it has to be seen entirely in some window negative m to m. Now let's suppose that sequence, the monotone sequence, is increasing. What does it converge to? At some point, it's going to have to level off because it cannot cross over the upper bound of capital M. Now, you might think, oh, it converges to its bound M. But remember, M can be any bound. That it doesn't have to be the tightest bound on the sequence. And so it turns out, as you might guess, it should converge to whatever the soup is of the values in your sequence. And we'll call this soup capital A. So to summarize this case, we can define the set A to be the set of all terms in our sequence. So let's write down what we know. So if A equals the set that contains all the values in our sequence, so it's all ANs, then we have two cases. When AN is increasing and bounded, that implies that AN converges to soup A. And an analogous picture would demonstrate that when AN is decreasing and bounded, AN should converge to the nth of the terms. So we will prove the MCT, and without loss of generality, we're going to assume that we are working with an increasing sequence, and we're going to show that the increasing sequence converges to the supremum of the terms. And so remember what convergence looks like. You put an epsilon band around what you're converging to, and you need to argue that there's a capital N, or a place to chop the tail that puts the sequence inside that epsilon band. Now, if you think about supremums and infimums and how we typically graph them, they are typically graphed on a number line. And remember, we have two different ways to depict convergence. We have the method the picture I've drawn here, but we also have the topological version of convergence that allows us to demonstrate that on a number line. Now, because supremums are best depicted on a number line, we're going to go ahead and use a number line to graph what's going on here and try to figure out how to set up our argument so that we can prove that an increasing sequence has to converge to its supremum of the terms. So here I'm going to draw us a picture. Now we have a bunch of terms in our sequence. So I'm just going to draw, let's see, we'll draw them in red. We've got A1, A2, A3. We're just getting closer and closer and closer to the supremum, like that. So what we need to do is we need to be able to specify an epsilon neighborhood. So this is V epsilon of sup A. And we want to guarantee that there's a place to chop our tail such that all of the values in the tail fall in this epsilon neighborhood. And so we've got this value here is like our A sub capital N. Now we can label the left and right endpoints of our epsilon neighborhood. So this is going to be sup A minus epsilon, and this is sup A plus epsilon. And our goal, show that a bounded increasing sequence converges to sup A. Now, we've seen a picture that looks similar to this before when talking about supremums. So the picture I've drawn is demonstrating convergence. That's our topological version of convergence. But we've seen this situation before where we have sup A minus epsilon versus sup A. This kind of looks like the lemma. So this picture looks like lemma 1.3.8 because we have sup A and we have sup A minus epsilon. So that's going to be an idea about how we might get our tail. So let's write out precisely what we want to show. We want to show that for all epsilon greater than 0, there exists a capital N in the natural numbers such that for all little n greater than or equal to capital N, A little n is in V epsilon of sup A. Now, another way to conceptualize being in this neighborhood is to say that we're looking for sup A minus epsilon to be strictly less than an, which is strictly less than sup A plus epsilon. So we're trying to show that inequality is met. Now, recall lemma 1.3.8. It says that for all epsilon, there exists a little a in your set A, such that sup A minus epsilon is less than A. But what does it mean for a number little a to be in our set capital A in this case? Remember what our set capital A is. We said capital A is the set of all the terms in our sequence. So if I'm saying there exists a little a in my set, what I'm really saying is A is just some term in the sequence. So A is equal to A sub capital N for some n in the natural numbers. Now I used capital N here. That is no coincidence. This ends up being a way we're going to get our capital N, but I also wanted to use a specific subscript because the value that the lemma returns is a specific number in A. So notice that this is already giving us part of the inequality that we were hoping to have. So we had our inequality sup A minus epsilon less than an was what we're trying to show for the left side in order to be in the epsilon neighborhood. And over here, we get that as a natural consequence of our lemma. Now, what about the other side of our inequality? Because remember, there's also the other side, less than sup A plus epsilon. Well, we get that for free because we know that we're dealing with the supremum here, and a supremum is an upper bound for our set, so any A that we're going to get has to be less than or equal to sup A, which is transitively less than sup A plus epsilon. So this lemma is the key to getting what we need. So why is it, if this is my capital N, why is it that after this capital N value, all of my ANs have to remain in this neighborhood? So why must every N such that N is greater than or equal to capital N be such that AN is in the epsilon neighborhood? Of sup A. Let's go back up to our picture here. What we've been able to do is we get an AN just using the lemma. So we get this AN right here by the lemma. Why is it that when I pick another term that comes later, so one of these guys or these guys, that I know I absolutely have to be in the neighborhood? What other condition do we have? Well, we know our sequence is increasing. So once AN makes it into the neighborhood, the rest of the values have to be larger than AN. And we know that they still have to be less than sup A because sup A is by definition of an upper bound for your set. So this has to do with since AN is increasing. So you have sup A minus epsilon. We know that's less than A capital N using our lemma. And then that value is less than or equal to AN using the definition, the definition of increasing. This is for N greater than or equal to capital N here. And then that has to be less than or equal to soup A. This is just using the definition of soup. And then transitively, that's less than soup A plus epsilon. So that's how we get in the neighborhood. Now, our argument kind of begs the question, where did we use our assumption that AN is bounded? Remember, we said that was a very important part of the MCT. That condition, together with increasing, has to guarantee that our sequence is going to converge. But it doesn't seem like we use bounded anywhere. So pause your video and think about that. Where did we use it? We used it to say that soup A even exists. So AN being bounded implies that the set capital A, which is the set of all my terms, is bounded. In particular, it's bounded above. And since this is a non-empty set, by AOC, soup A has to exist. And now that we know it exists, we can use its properties to show that our sequence has to converge to soup A. So let's write up the proof of this. So this is the proof of the MCT. And without loss of generality, we are going to assume AN is increasing. If AN was a decreasing sequence, we could use the same argument, but for infimums. And we could use the lemma for infimums to get our tail. So we're going to let capital A be the set AN. Since AN is bounded, A is bounded above. And then because A is non-empty, the AOC, the axiom of completeness, says soup A exists. We will show that AN converges to soup A. Now to do this, we're using the definition of convergence. So we need to introduce an arbitrary epsilon. We're going to let epsilon be greater than 0. And now we have to argue why there's a capital N. How do we chop our tail? We said this capital N comes from the subscript of the value that the lemma returns to us. So we want to say by lemma 1.3.8, there exists a capital N in A such that when we look at soup A minus epsilon, that is strictly less than a capital N. So now I have my capital N. Notice here, capital N is just a natural number. I've introduced it. And now I can say, so for all n greater than or equal to capital N, we have soup A minus epsilon is less than a capital N, which is less than or equal to AN. And this is using the definition of increasing here. This is using the lemma. Then that's less than or equal to soup A. That's using the definition of soup. Which is strictly less than soup A plus epsilon. So what we've really shown here is that little a(n) is in the epsilon neighborhood of sup A. And that's the topological definition of convergence. We've shown that the entire tail is in there. The fact that we are dealing with subscripts greater than or equal to capital N lets me use the increasing factor, because I know that the values, the little n's are subscripts that are coming after capital N, and so my sequence only has to increase in size. And so by definition, a(n) converges to sup A. And we're done. Just an important remark, we can actually say, we can restate the MCT as an if and only if statement. So the MCT can be restated as a monotone sequence converges if and only if it's bounded. Now, the backwards direction of this statement is just the MCT. And then the forwards direction saying, you know, if you converge, then you're bounded, that's just the converge implies bounded theorem that we've already demonstrated. So if you are being asked to prove that a monotone convergent or a monotone sequence converges, really what you're being asked to do is prove that the sequence is bounded. Let me write that down. When asked to show that a monotone sequence converges, prove instead that the sequence is bounded. So you don't have to prove a monotone sequence converges by definition. You can just demonstrate it's bounded, then apply the MCT. And that's it.